All right. Chemistry 3101. This is chapter 3. Moving right along here, dealing with acids and bases. And I know that many of you have just completed General Chemistry 2, probably the past semester, this past spring semester. And so in that class, there's a huge focus on acid-base chemistry. So I just kind of want to introduce you this morning to the concepts of the definitions of acids and bases. It'll probably be a refresher for most of you. All right, so let's get into what's called a Bronsted Lowry acid and a base. So, put simply, the Bronsted Lowry definition of an acid is something that donates a proton. Right? What's a proton? A proton is nothing more than a proton, right? If you think about a hydrogen atom, what does a hydrogen atom consist of? It's element number one. It's got one proton in the nucleus, right? And it's got one electron. So if you remove that one electron, what have you got? All you have is the nucleus, which is a proton. So an acid donates a proton, which is H plus, whereas bases accept a proton, okay? So you have to know that an acid donates a proton and a base accepts a proton. You think about acids. If I was to ask you, what's your favorite acid from chemistry class, you'd say, oh, Mr. Dion, sulfuric acid, nitric acid, right? Hydrochloric acid, right? These are acids that come up all the time. So here's a classic example from where? From general chemistry. If you take hydrochloric acid, okay, if you take HCl, you put it in water, what do you actually have? Okay, do you have mostly HCl in solution or do you have mostly hydronium? Well, the answer is you have mostly hydronium. Okay, let me prove that to you, because what is the purpose of an acid? Right, the purpose of an acid is to donate protons, and it's going to do its job when it can. So if you have HCl, which is a proton donor, it's going to donate that proton to water, which will behave as a base. Water can behave as a base or an acid depending on the situation, but here it's accepting a proton, so it's behaving as a base. Then you're left over with a chloride ion, which is a conjugate base, and you're left over with hydronium, H3O plus. You should remember that that's called a hydronium, which is the conjugate acid. Now, in terms of a conjugate acid and a conjugate base, if you ever get confused as to which one is which, just look at the reaction in reverse and say, what is the chloride doing? The chloride is becoming HCl if I look at the reaction going backwards. So if it's becoming HCl, that means it's accepting a proton. What's a proton acceptor? A base. Therefore, chloride must be a conjugate base. If you get confused about the hydronium, well, usually students remember that hydronium is an acid because you see it so much in general chemistry too. But again, if you've forgotten or if you get stuck, what's the hydronium doing? Well, it's becoming water. So what does that mean? It means it's losing a proton, or it is donating a proton, and therefore it is a conjugate acid. So you have to know conjugate acids, conjugate bases, and you also have to be able to label an acid and a base. All right. So again, the conjugate acid is what results when the base accepts a proton. We saw that it was hydronium in the previous example. A conjugate base results when an acid gives up a proton. So I'm going to give you a second, and I want you to try to label the acid base and the conjugate in this example shown here. I'm going to give you a second to take a look at it. Could anybody tell me what water is behaving as here? Is water behaving as an acid or a base in this reaction shown down here? Yeah, absolutely. Water is behaving as an acid, isn't it? Yes, you're all correct. Right? Water is behaving as an acid, which means that this tert butoxide is behaving as a base. Right? How do you know that? Because the water is donating this proton, which ends up on the base. So that means that when the base accepts a proton, right, I end up with a conjugate acid. So that means that this is my conjugate, can spell. This is my conjugate acid. And my hydroxide ion, that's my conjugate base, isn't it? Right? Conjugate base. Because the conjugate base is what results when the acid liberates or donates a proton. So again, you've got to be able to label an acid a base, a conjugate acid, and a conjugate base, okay? And you can see I could ask a question about that really easily. Well, if you remember in chapter 2, we looked at curved arrows involved in resonance. However, we didn't look at any reaction curved arrows in chapter 2. There was no reactions, only resonance. We were only showing the delocalization of electrons around molecules and ions, right? We had nothing, there was nothing to do with reactions. Well, this is a reaction right here, isn't it? Right? That's an acid-base literal reaction. There is a bond being broken, right? This bond is being broken in the reaction, and this bond is being formed in the reaction. And so now what we're going to do is we're going to take those curved arrows and we're going to use them to demonstrate the flow of electrons in an actual reaction. So that's why section 3.2 is titled Curved Arrows in Reactions, because we haven't looked at that yet. We only looked at curved arrows involved in resonance. So the making and breaking of bonds involves literal electron movement, and we can use curved arrows to describe the flow of electrons in a reaction. They're the same type of curved arrows that we used when we drew resonance structures, right? Each double-headed arrow represents the flow of 2 electrons. This arrow represents the flow of 2 electrons, right? The tail of an arrow should always start on a pair of electrons, either a lone pair or a bond. It should end up on an atom or on a nucleus or in between, 2 atoms. But here, these curved arrows are very different from the curved arrows that we looked at in chapter 2. Why? Because they're actually showing the movement of electrons. Remember, when we looked at resonance structures, you've got to be able to separate this in your mind. We weren't talking about the electrons buzzing around and vibrating around the molecule. That's not what's happening. Resonance structures are used to show how the electrons are delocalized over an entire molecule. They're used to give you a full 30,000-foot view of a molecule, whereas now we're using the arrows to just show a reaction occurring. And we call these reaction arrows, when we draw these reaction arrows, I should say, we call this a reaction mechanism. And learning to draw reaction mechanisms is one of the most valuable and one of the most powerful tools that you will learn in this class. It's imperative that you know how to draw curved arrows in reaction mechanisms. Let's take a look at a specific example instead of the generic example that was on the last slide. Here you have hydroxide. Again, organic chemists love to leave spectator ions out. It might be sodium hydroxide. It might be potassium hydroxide. The cation is neither here nor there. But here our base is reacting with our acid. This is acetic acid, the same acetic acid that's found in vinegar. So we have the base that is taking a proton from the acid. We're forming water as our conjugate acid, and we're left over with this polyatomic ion, which is an acetate ion. So this is called the acetate ion, and you would have seen that in general chemistry too. Anyhow, so what's happening here? We have a curved arrow that's starting on a pair of electrons from the hydroxide. Why? Because the hydroxide is the base. It's the proton acceptor. So when it accepts that proton, it's going to form a bond to the proton. A proton is H+. There are no electrons in a proton. So the proton doesn't have any electrons to bring. The electrons have to start or come from the hydroxide, and then the tip of the arrow ends up on the proton, and that shows the bond being formed between the oxygen and the hydrogen. So this is bond, we'll say here, bond formed, right? But what's going to happen to this pair of electrons? They're not just going to be left dangling out in outer space. That pair of electrons, that represents, or this curved arrow represents a bond being broken, okay? And you can see that the tip of the arrow or the head of the arrow is ending up on the oxygen, directly on that oxygen, right? So now the oxygen has 3 lone pairs and a sigma bond, so it has an overall -1 charge, which results in our conjugate base, the acetate. The vernacular that you're going to hear me use in organic chemistry is the base is attacking the acid, and that is not something that I made up. That is that's how we describe it in organic chemistry. We say the base is attacking the acid. It's using the pair of electrons to do that. The acid can't lose a proton without a base taking it, right? All acid-base reactions occur in one step, meaning that both of these steps occur simultaneously. All right. So again, the 2 arrows show the movement of 2 pairs of electrons moving simultaneously. You have a bond being broken and you have a bond being formed in this acid-base reaction. So whenever you draw curved arrows in an acid-base reaction, you're going to draw two arrows simultaneously, right? You're going to draw one that represents a bond being formed, and then you're going to, you're going to draw another one that represents a bond being broken. All right. Let's take a look at a question. It says, all of the following acid-base reactions, and there's only one here that we're going to study in greater detail, or I guess we will look at other ones. Reactions that we're going to study, yeah. For each one, draw a mechanism and then clearly label the acid, the base, the conjugate acid, the conjugate base. I mean, we could start at several different points here. You know where I would like to start with a problem like this as your instructor is, let's draw on any lone pair that's missing. You know, that's where I would start. This oxygen on this phenol is missing 1, 2 lone pairs. The hydroxide is missing 3 lone pairs. This phenoxide is missing 3 lone pairs, and the water, the oxygen here, is missing 2 lone pairs. So that's the first thing I like to do, because you've got to have your lone pairs drawn in to draw a mechanism correctly. Now, you'll see later on in our textbook that there's a little blurb in the textbook where he says, if you watch a seasoned organic chemist, you know, talking with another organic chemist, oftentimes they will leave lone pairs out, okay? And he says you can even try that yourself. I do not recommend doing that, okay? I have kind of a mantra when you're teaching organic chemistry, when you're just learning the subject, friends, don't let friends leave lone pairs out, okay? Make sure to include those. All right, if I call this, let's keep it simple here. If I call this, I don't know, number 1, and I call this number 2. Can anybody tell me which one of these is behaving as the base? Would it be 1 or 2? And it's not a trick question. Yeah, absolutely, Kyla. Yeah, I think you're all getting the hang of it here. It's number 2, right? You know, generally speaking, when people who've studied chemistry for a year, which you all have done, when they see a hydroxide, they think, yeah, it's probably the base, right? Yeah, absolutely. So this is my base, which means that this is behaving as my acid. Okay. And how do you know? The acid is giving up a proton. It has it here, but it doesn't have it over here. So what does the acid become after it donates a proton? It becomes a conjugate base. And what does the base become after it accepts a proton? It becomes the conjugate acid, like that. Now, if we want to draw some curved arrows, well, we have to draw a curved arrow starting on a lone pair from the hydroxide. You can start on that one. You can start on this one. You can start on that one. Sometimes students will start on the negative charge. I don't do that. You should always start on a pair of electrons, and then you're going to draw a curved arrow over to the hydrogen atom, because that's the proton that's being picked up. But what's going to happen to this pair of electrons is that they're going to end up on the oxygen. You can draw them like this. You know, if my students are like, well, can I draw it like that? Sure. You can technically, I wouldn't do this, but you could do it like that. Technically, it's not incorrect. It looks ridiculous, okay? But there's a lot of things, there's a lot of leeway you have with the way you draw curved arrows. You know, the first curved arrow, now I'm being ridiculous here. I'm kind of being silly, but you could literally draw, you know, this, say, there you go. Now I picked up a proton. Follow that curved arrow, buddy. Well, there's nothing, I mean, technically it's correct. It does show the flow of 2 electrons, but it's just a little ridiculous. Okay, so we try to draw the neatest arrows that we possibly can, like that. And there you go. Give me a thumbs up if you follow me on that one. The curved arrows in that acid-base reaction. Okay, great. Great. I see one person. Okay, I see a bunch of you follow me. Good. Well, with that in mind, let's try a couple more. Let's switch over to my blank document. Where was it? Which I'm probably running out of space on. Oh, do I have no space left here? Uh-oh. Uh-oh. Here we go. There's some blank space. All right, I want to try another one with you. So I love it when my students learn bond line structures. It just makes life so much more enjoyable. So if we take this molecule and we react it with this ion, there we go. And we're going to draw this. And I want you to try to draw this out. I know that it's time consuming, especially when you're learning the subject, to draw curved arrows and to draw structures out. I know it's a bit of a PITA, but I'd like you to try it. So we'll do this one, and then we're going to do this one too. So we'll do a couple of examples here. just to get in the habit. You know what? I'm going to see if you guys can draw the curved arrows for this one and also draw the products. I'm going to give you a minute. I actually need to get a drink of water. I didn't get one when I went upstairs. So just give me 2 shakes of a lamb's tail and we'll come back. So again, for this one, I want to see if can you draw the products and the curved arrows? It's kind of a double whammy. All right, in the first one, if I label these 1 and 2, could anybody tell me which one is behaving as the base in this one? It'd be 1 or 2 is behaving as the base. And it's not a trick question. Mr. Dion doesn't like trick questions. Yes, yes. See, my students are faster than me now. Okay, so acetone is behaving as the base. Yes, hydronium is behaving as the acid. What's left over from the conjugate acid is going to be the conjugate base, which would be water in this case. And here we have this protonated ketone, which would be our conjugate acid, which is surprisingly acidic, and we'll discuss that later on. Now, if we want to draw some curved arrows, well, this is the proton in question, right? And if you're like, well, Mr. Dion, couldn't it be this one? Or couldn't it be this one? That's neither here nor there. They're all identical. I'll just go with the low-hanging fruit, the one that's the closest to it, right? So let's start by drawing a curved arrow. So we're going to start, if we're making a bond between the oxygen and a proton, I'm going to need a pair of electrons from the oxygen, and I'm going to take that proton. Now, if my oxygen over here has 2 lone pairs, but here it only has 1, where did that other lone pair come from? It came from this bond being broken and the pair of electrons going on the oxygen. Give me a thumbs up if you got those curved arrows, if you drew those, correctly. Is anybody with me on that? Yes, good. Okay, great. Not simple, right? It's not a joke, right? Drawing curved arrows is not, I was going to say not for the faint at heart. Well, I don't know about that, but it's not a simple thing, right? If it was simple, remember, if it was simple, everybody off the street, anybody on the street could do it. So it's not simple. All right, let's take a look at another one here. And this is the last one we're going to take a look at. This compound here is called benzoic acid. Benzoic acid. It's a carboxylic acid, obviously. And it's got an aromatic ring. It's a white solid. And then here we have hydroxide. Hydroxide. Could anybody tell me who's behaving as the base here? Would it be the hydroxide or the benzoic acid, do you think? Yeah, absolutely. Absolutely. Thanks, Mackenzie. So, look, even if you weren't 100% sure about what to draw, because I told you, I'm going to ask you to, do problems like this where you actually have to draw the product. Well, if this is my base, okay, and if this is my acid over here, then my base is going to take a proton, right, like this, and then this bond is going to break. So I'm going to be left over with water for one thing, right, which will be my conjugate acid. And I'm going to be left over with this, which is called a benzoate. There we go. If you look at foods, you'll see benzoates in them all the time. And this is our conjugate base. Like that, just like that. There you go. So now you've got your first, your initiation to drawing not only curved arrow mechanisms, which is kind of a big deal, but also, looking at acid-base reactions. And we look at, almost Avogadro's number of acid-base reactions in organic chemistry. They come up constantly, constantly. So if you ever get confused on your curved arrows, and if you ever draw a curved arrow backwards or something like that, remember that the tail of the arrow will always start on a pair of electrons, right? If you think about this mechanism, maybe, right? You see the tail starts on a pair. The tail here starts on a pair where it's a bond, right? The tail here starts on a pair. The tail here starts on a pair like that. All right. And then the head of the arrow is either going to end on a nucleus or on an atom, or it's going to end up between two atoms if you're making a bond. All right. All right. If you're making a pi bond, I should have said. Anyhow, there we go.